You ever look at a really complex function and just wonder what it actually looks like? I mean, sure, you could plot a million different points and try to connect the dots, or you could use a little bit of calculus to basically become a detective, uncover its hidden story, and sketch its exact shape with just a handful of clues. Today, we're putting on our detective hats.
So here's our case file for today. This function, f of x, might just look like a string of letters and numbers, but trust me, it's hiding an entire journey full of peaks, valleys, and some pretty dramatic turns. Our mission is to map out its entire adventure, step by step. So how in the world do we crack a case like this? Well, like any good investigation, we need the right tools. And in calculus, our main investigative tools are derivatives. These guys are going to give us every single clue we need to figure out this function's hidden shape. To be specific, we're going to be using the first derivative to find out where the graph changes direction, and then we'll use the second derivative to understand how it curves. These two tools, they're the key to unlocking the whole mystery. Okay, our first move is to find the most interesting places on the map. You know, the spots where the function might be hitting a high point or a low point. This is where all the action is. These points of interest have a special name, critical points. They're the spots where the slope of the function, which is just the first derivative, is totally flat, or zero. Think about it. The very top of a hill or the bottom of a valley. The ground is momentarily flat, right? These are our prime suspects. All right, so we found our suspect points. But what are they, really? Are they local maximums, the peaks on our graph? Or are they local minimums, the valleys? We need a way to figure that out. So, we actually have two ways to interrogate these points. The first derivative test checks the slope around the point. But honestly, my favorite is the second derivative test. It's just so much more direct. If the second derivative is negative, it means the graph is frowning, so we've got a peak, a local maximum. If the second derivative is positive, the graph is smiling, which gives us a valley, a local minimum. Pretty simple and kind of fun, right? Now, we know about the peaks and the valleys, but what about the shape of the graph in between all those points? Well, this brings us to our third and final clue, the nature of the curve itself. This is something we call concavity. Basically, is the function curving up, kind of like a bowl that's ready to hold water? That's concave up. Or is it curving down, like an umbrella shielding you from the rain? That's concave down. And what tool tells us all this? You guessed it, our friend the second derivative again. Positive for up, negative for down. And here's the really important part. That exact moment when the graph switches from being concave up to concave down, or the other way around, we call that an inflection point. It's where the function's whole mood changes, and it happens precisely where the second derivative equals zero. All right, we've got our clues, we've got our tools. It is time to put it all together and finally solve the mystery of our function. Let's do this. We're going to follow a really clear three-step game plan. First, find those critical points. Second, we're going to test them to see if they're maximums or minimums. And third, we'll find out where the curve changes its bend. Let's get to it. Step 1. Find the critical points. So we take the first derivative, set it equal to 0, and boom. It gives us two key locations on our map, x equals 3 and x equals -1. These are our two prime suspects. And now for step 2, let's interrogate these 2 points. To do that, we need to bring in the big gun, our second derivative. This is the tool that's going to tell us if we found a peak or if we found a valley. And the results are in. They are crystal clear. At x equals 3, the second derivative is positive. And positive means smiling, so that's a local minimum. Then at x equals -1, the second derivative is negative. Negative means frowning, so that gives us our local maximum. Just like that, we've classified our points. On to our final step, finding that inflection point. Where does the curve change its whole personality? We set our second derivative to 0, and the math gives us just one potential spot, x equals 1. And this is the exact turning point for the curve's shape. If you check any point to the left of x equals 1, the second derivative is negative, so the graph is concave down. Check any point to the right, and it's positive, so the graph is concave up. Since the concavity changes right there at x equals 1, it's official. That's our inflection point. And we've done it. We gathered all the clues, we followed all the steps, and now we can finally assemble the complete case file on our function. The mystery is solved. So here it is, the complete story. We have a local maximum at x equals -1. We've got a local minimum at x equals 3. The graph is concave down all the way up until x equals 1, and then it flips, and it's concave up forever after. And that inflection point ties the whole story together. We now know exactly how this function behaves. And that's really the big takeaway here, isn't it? We started with what looked like just a random jumble of algebra, but by systematically applying the tools of calculus, we've turned it into a predictable story with a clear shape and really well-defined features. That is so cool.
So I'll leave you with this question to think about. If we can so clearly map out the entire journey of just a single function, what other mysteries out there could these same tools unlock? I mean, from optimizing a business to plotting planetary motion, the same core ideas apply. The only question is, what are you going to uncover next?